What specific problem does the physics IQ dataset aim to address in evaluating video generative models? Please explain the significance of using real-world videos instead of synthetic ones.
The physics IQ dataset aims to address the problem of evaluating the physical understanding capabilities of video generative models by providing a benchmark that utilizes real-world videos rather than synthetic ones. The significance of using real-world videos lies in the fact that synthetic datasets often introduce a real vs synthetic distribution shift, which can confound results when testing models trained on natural videos. By capturing diverse and complex physical phenomena through 396 videos of 66 different scenarios, the physics IQ dataset allows for a more rigorous assessment of how well models can predict physical events, such as collisions and fluid dynamics, in realistic settings. This approach helps to measure the model's understanding of physical laws more accurately, as it incorporates the inherent variability and chaotic nature of real-world interactions. Ultimately, the dataset provides a more reliable foundation for evaluating and improving the physical reasoning capabilities of generative video models.
How does the validation protocol for the physics IQ benchmark work? Illustrate the process step by step, including the conditioning videos and their role in testing the models.
The validation protocol for the physics IQ benchmark involves several key steps to evaluate the physical understanding of video generative models. First, an 8-second video containing a physically interesting event is selected, which is then split into a 3-second conditioning video and a 5-second test video that serves as the ground truth. The conditioning video is provided to the model as input, either as the full 3-second video for multi-frame models or as a single frame, the switch frame, for image-to-video models. The switch frame is carefully chosen to ensure it contains sufficient information about the physical event, while requiring the model to understand physics to predict the continuation accurately. Finally, the model generates the subsequent frames based on the conditioning input, and its performance is evaluated against the ground truth using various metrics that assess different aspects of physical understanding, such as spatial IOU and spatiotemporal IOU.
Can you provide a concrete example of how a specific scenario from the dataset, like the domino chain reaction, is used to assess a model's physical understanding? Walk through the steps involved in this scenario.
In the physics IQ dataset, the scenario involving a domino chain reaction with a rubber duck interrupting the chain serves as a concrete example to assess a model's physical understanding. The evaluation begins by presenting the model with a full 8-second video of the scenario, which is then split into a 3-second conditioning video and a 5-second test video that acts as the ground truth. The model is conditioned on the last frame of the 3-second video, known as the switch frame, which captures the moment when the first domino is tipped but has not yet contacted the second domino. This setup requires the model to predict how the chain reaction unfolds, specifically that only the dominoes to the right of the rubber duck should fall, while those to the left remain stationary. The model's performance is evaluated using metrics such as spatial IOU, which measures whether the location of the action, the falling dominoes, matches the ground truth, and spatiotemporal IOU, which assesses both the timing and location of the actions, thereby testing the model's understanding of the physical principles governing the scenario.
What are the 4 metrics used to quantify physical understanding in the physics IQ benchmark, and how does each one contribute to the overall assessment of a model's performance?
The 4 metrics used to quantify physical understanding in the physics IQ benchmark are spatial IOU, spatiotemporal IOU, weighted spatial IOU, and mean squared error, MSE. Spatial IOU assesses where actions occur in the generated videos compared to the ground truth, focusing solely on the location of movement. Spatiotemporal IOU extends this by evaluating both the location and timing of actions, ensuring that actions not only happen in the right place, but also at the correct time. Weighted spatial IOU measures both the location and the magnitude of actions, distinguishing between different types of motion, such as repeated versus single occurrences. Finally, MSE evaluates pixel-level fidelity, penalizing models for unrealistic changes in object appearance, thus complementing the other metrics by ensuring visual accuracy. Together, these metrics provide a comprehensive assessment of a model's ability to understand and replicate physical principles in video generation.
What were the main findings regarding the performance of the evaluated video generative models on the Physics IQ benchmark? Highlight any significant trends or surprising results from the experiments.
The main findings from the evaluation of video generative models on the Physics IQ benchmark revealed a significant gap in physical understanding, with the highest scoring model, Video Poet Multiframe, achieving only 24.1% of the possible 100% score based on physical variance. Notably, multiframe models generally outperformed their image-to-video counterparts, indicating that access to temporal information aids in predicting future events. A surprising result was the strong performance of stable video diffusion in the weighted spatial IOU metric, despite its struggles with spatial and temporal accuracy, suggesting that it generates more action but often in a physically implausible manner. Additionally, the study highlighted a stark disconnect between visual realism and physical understanding, as models like Sora produced visually appealing videos but lacked coherent physical interactions, demonstrating that high-quality visuals do not equate to a grasp of physical principles. Overall, the results underscore the need for further advancements in model training to enhance physical reasoning capabilities.
Discuss the limitations identified in the proposed method. What aspects of physical understanding do the current models fail to capture, and how might this impact their applicability in real-world scenarios?
The proposed method identifies several limitations in the current video generative models regarding their understanding of physical principles. Notably, all evaluated models, including the highest-scoring Video Poet Multiframe, only achieved a score of 24.1% against a physical variance baseline of 100%, indicating a significant gap in their ability to comprehend real-world physics. The models often fail to accurately simulate physical interactions, as evidenced by instances of objects passing through one another or generating implausible continuations, such as a candle appearing spontaneously in a scenario involving a matchstick and water. This lack of physical understanding can severely impact their applicability in real-world scenarios, as the models may produce visually appealing but physically unrealistic outputs, leading to potential misinterpretations in applications like robotics or simulation. Furthermore, the absence of a correlation between visual realism and physical understanding suggests that generating realistic-looking videos does not equate to a true grasp of the underlying physical laws, which is crucial for tasks requiring reliable predictions of physical behavior.